Hello, hello. Okay, hi, this is my first time here. My name is Anna Borovikov. I work at NASA at Goddard Space Flight Center down in Maryland. I work at Global Modeling and Assimilation Office. The picture on the title, of course, shows the splashing of the warm water along the equator in the Pacific Ocean, the very nice representation of the El Nino, and I will tell you a little bit more about who made it a little later. So moving along. Okay, up there is a direct quote from Dorian's email when she asked me to participate. She said, please answer this if you can. How can you tell if El Nino is changing from one phase to another? What is the current status and why we were thinking we were going into La Nina and now we're thinking something else maybe. So I took it quite literally, so I will spend some time telling you how we are able to say anything about El Nino at all, and then what state we are in right now, and why we had changed our mind about it, and at the end I will tell you about something else. Then a little cartoon about how we operate. Okay, so in order to say something about the state of the uh, Earth's climate, we really need a lot of people's input, and I really forgot to say on the front, on the title page, I had lots of names, but there should have been more. They will never fit, and I don't know everybody who's contributing uh, to to um, to the research and to our understanding about the climate. So what I have on this slide is one of three key ingredients to the climate research. We all hear about models, numerical models, and what I do is in order to make in order to understand the state of the climate, in order to make a prediction, I run what's called a coupled climate model, and by coupled I mean is that I have several components, and they're depicted, sort of depicted here, but I will tell you one is the model of Earth's atmosphere, the other one is the model of Earth's oceans with a model of sea ice in there. We also have the model of land surface hydrology, and this is this little piece there. It's very interesting. It's well, I will tell you about numerics maybe some other time. So in order to make a climate forecast, we have to make all these models fit together. They all quite complex. Each one of them is subject in numerical modeling. So up on the left, I have two examples as to how we can put the real world into the computer. So this is a representation of the numerical grid that we have for the atmospheric model. It is something that's called cube sphere. So in order to discretize our spherical atmosphere, we put it on the little sort of three-dimensional chunks like that, and then each one will go in a separate processor, and then they will all be sewn together. So there are a lot of great, bright minds that work on really the numerics of the modeling. This other picture is of the grid that we use for the ocean model, and it looks a little bit funny if you look very closely. This is the two North Poles, because we actually have ocean on the physical North Pole, so we don't want to have a discontinuity in our numerical model. So it's a little creative, like done like this. And here on the right is a photograph of our great supercomputer that is just absolutely critical to the work we do. So, so the models. So keep that in mind. We really need very good numerical representations of the climate. So moving on to the next slide, and of course models are not enough. Models have to be aware of the. All right, so next we need observations, and of course being at NASA, everybody thinks, okay, we have this great suite of satellites orbiting around the Earth, so we should by now know everything about our planet. And we do. We know a lot about Earth's atmosphere. So this is just a great picture of all these satellites that are up there. This down below is a figure that represents the transparency of the atmosphere. So we can find certain frequencies that can come all the way through, that can penetrate the atmosphere all the way through, like all the microwave range, for example. So, in fact, we can observe Earth's atmosphere very well all the way throughout. We can understand its composition. And up here on the right is an example of how much data comes in and goes into our analysis of the state of the atmosphere from different sources, different satellites, but just look at this number. It's millions every 6 hours. And down here is, of course, what I'm going to be talking about next. A big problem. We can only see through the atmosphere, but then pretty much everything gets reflected on the Earth's surface, and we cannot penetrate below the surface of the ocean. So let's talk about the oceans. And we have to talk about the oceans because when we talk about the climate, ocean is at the core because of its heat capacity, because anything that, any process that happens long term, and by long I mean weeks, months, years, is determined by the state of the ocean. El Niño being a grand example of that. So let's look at what kind of data we have at the ocean. All we can see from the satellites is sea surface temperature and sea surface height and ocean color, which has to do with the living beings in the ocean, with biology, plankton and all that, which is also important. But we cannot see anything below the surface. And if you look at, if you look at these two figures on the left, in orange and purple dots are the points where we have data that is going down to maybe 500,000 meters, what we call a profile data, measurements of temperature and, if we're lucky, of salinity of the ocean. So over 5 years, this is all we had. 5 years, most relatively recent years, 1999, 2003, orange ship tracks, and purple dots are some instruments that are expandable, that are thrown in the water and they drift with the ocean currents. So what to do about it? In the most recent years, more work was done with creating really inexpensive but reliable instruments that can just be thrown in the water, and this is one example of such an instrument called an Argo float. And the way it works, it floats with the ocean current, and then it has a little tiny battery in it, so it actually submerges. It goes down to 2,000 meters and then comes up, and as it goes down and comes up, it takes measurements and transmits them via satellite back to the collecting point. So in the next 5 years, we had a lot more measurements. So you can see we pretty much covered the Pacific Ocean, which is great. And very important, very important data collection activity that I wanted to tell you about is this tau tridon array. These are permanent buoys that were put at different locations along the equator in the Pacific Ocean, and a buoy looks like this. It has a string attached to it. It's anchored at the bottom, and it goes down to 2,000 meters, and it takes measurements all the time, every minute, say. So first buoys were put out in the early 80s, and that what really contributed to our understanding of the El Nino. That was the first look into the depths, into what's happening in the subsurface. They are very important. Unfortunately, they're getting old. They're very expensive to operate, but we really, really, really need them. But remember the number from the previous slide, millions per 6 hours. We're lucky if we get tens of thousands of observations per month. Look at this figure down here below. This is depth. These are years only. In the most recent years, we started to see what's happening in the ocean down below us. And up here is representations of different data that are used in our research, and there are only two streams that are from satellite, and they are both are surface only. So we still desperately need to figure out a ways to observe our oceans better. There's a lot of there down below. So now we talked about the models, we talked about data, and now I'm going to talk about the third part, is something called data assimilation, and that's the way to marry the two, because we can create perfect models, create a perfect virtual climate that lives in the computer, but it is not aware of the conditions today. And in order to make a good forecast, we have to make sure that our models are as close to the actual state of the ocean and atmosphere as possible. And that's where data assimilation comes in. And that's a whole big, very important subject of applied mathematics, of numerical analysis. So here on the right, I have a little schematic explanation as how you can think about data assimilation. If you have a model and if you have data points, you want to come up with a model realization that will pass as close to the data points as possible. So you can think about it as an interpolation with the function, except for I have not, 3 or 4 or 5 data points, but tens of thousands and even millions of them. And another complicated factor is that and I say I because this is actually my subject of work. I'm working in oceanographic data assimilation. So I got the model, I got the data, and my responsibility is to initialize the model with the data, so to assimilate the data into the model. And in the ocean, we need to know temperature and salinity. Ideally, we want to know currents. Usually, we observe only temperature. We sometimes get salinity observations, but we want, in order to properly assimilate data, we want to understand how inserting one observation into one location, changing temperature to what we observed it should be, how it will affect the rest of the field, temperature elsewhere, and salinity elsewhere, and currents elsewhere. So we have to adjust our model so that it is very close to the data, but yet it is consistent, and all the physical and all the dynamical processes there are not disrupted. And that's what this picture on the left shows. It's an example. If I have a single observation, put the temperature observation, raise the temperature by 1 degree, this is how the surrounding area is going to be affected in the horizontal and also in the vertical. So that's it. in terms of how we do it. So every um, every month we run our big coupled model in order to produce a seasonal forecast, which means outlook 6 to 9 months out into the future. That's how we can try to tell what's going to happen. So every month I get all the data available up to that point. I run all the simulation scripts and come up with the ocean state that I think is representative of today's state. Not just the ocean, but everything. Sea ice, atmosphere, and soil hydrology. So now let's move on to the current El Nino conditions. So on the left, you see the time series of sea surface temperature anomaly, meaning deviations from the mean, for 4 different regions that are traditionally looked at. You probably know all about them: Niño 3, Niño 3.4, and so on. These are from our model and the observations. The data starts back in 1982. That's when we started our model first, and we always overplot the observations to make sure we uh, represent the current conditions well. And so this is, you can see again when we had the huge El Niños, 82, 83, 97, 98, and the most recent one. And on the right is the zoom in to the last year. So this is up to present. So we are coming out of the big El Nino, and now the sea surface temperatures are very close to neutral conditions. But this is not the end of the story. When I said I'm initializing the ocean, making sure that the model state is as close as current as possible, I can never be sure that it is the best realization, because we just don't observe everything everywhere. So what we do, we run what we call ensemble forecasts, meaning we have several equally possible realizations of the state of the Earth's climate. And then ensembles run at different research centers, get collected together and looked at together by, say, for example, this institution, IRI, which puts together the North American multi-model ensemble. So right here you see the point of initializing the forecast, and then everybody sends in their predictions of the sea surface temperature anomaly. So here we're looking at Niño 3.4 region again. And having those multiple equally probable realizations give us a way to provide an uncertainty with the forecast. We can have an estimate as to how sure we are as to what's going to happen. And that what is shown here below is the probability based on this grand ensemble of ensembles of predictions as to what's going to happen. So right now it looks like going into next year, the neutral conditions have the highest probability. There is a chance that we may go into La Nina. There's even a tiny chance that we may go into El Nino. But right now, our predictions are such that we're thinking we're going to stay close to zero. And quickly on the left is the evolution of the subsurface temperature. So it's a cut across the equator in the Pacific Ocean. So this is a year ago, and time goes down. So it was very warm in the east, and you can see how the state of the ocean evolved. Now we're moved out of El Nino, so this is the current state, and this is the forecast from our model. So we're going to stay, right now we're cold, and then we're going to stay sort of maybe a little lukewarm, but the surface is going to be neutral. But take that with always with understanding that with the seasonal forecast, with the climate forecast, you always have to think that it's a probabilistic forecast. There's an uncertainty associated with that forecast. And the last question is why we were saying it's La Nina and now we're saying it may not be, because when we started talking about La Nina, it was back maybe in February, March, May, and all forecast who, all forecasters who work in this business of seasonal forecasting know about a phenomenon that's called a spring barrier. It's very hard to make a prediction about the state of the Pacific Ocean past the spring, past the February, March, April, May, and uh, this is this four bottom plots correspond to four different El Nino regions, and they show the model, the forecast scale. So if we initialize our forecast in December and we look out, so we look out in months of January, February, we have very good scale. As soon as we get to March, our model is very unsure. It doesn't do predictions of the spring conditions very well. So if we initialize our forecast in spring, then right away we really are not able to say what's going on. And one of the reasons why is because during the spring, usually the Pacific Ocean is very quiet. The processes that happen there are on a very small scale, and those are very hard to capture. When something grand like an El Nino happens and the signal is thrown, all models do very well. So that may be one of the reasons why we were thinking it was going to be La Nina, but as we moved past this spring, our forecasts become more certain, and we're actually now thinking it's going to be neutral conditions. And that's another way of representing the sea surface temperature anomaly. So these are our most recent forecasts. We are sort of saying we're going to stay around zero. All right, but what I wanted to finish with is, yes, El Nino is a very, very important phenomenon. It's a global scale, as Dorian was saying, determines weather patterns all around the world. But this year, we cannot talk about El Nino out of context of another big event that's happening, and it's something that is now being sort of officially termed the Blob. And it's a warm temperature anomaly in the let's see, can I get the point? In the northern Pacific Ocean. This is something that has never happened before. This is the picture, a figure of 2013, September 2013, and it stayed there ever since. This is 2014. 2015, this is current condition, it's still there. So this blob interacts with El Nino, and it actually alters the weather patterns that are usually believed to be results of El Nino teleconnections. And this is something that wasn't there as far back as we have been observing ocean temperature. So this is something to look for. This is something that we're trying to understand. So just in addition to El Nino, keep an eye on the blob. And I will stop there. This is the website of our office. There's lots of information about the current state of the climate.